let's first investigate the behavior of their first solution defined by the first of our contours. So here it is. It's defined up to some multiplication constant, a1, which is to be defined later. So e2 plus t squared over 2 dt. Okay, so first of all, let's normalize this solution. Before we do so, we noted that the most crucial part of this contour, or peculiarity of this contour, is that it can move freely in the complex plane. The only significant condition which is imposed on this contour is that its endpoints lie at the allowed regions, so-called allowed regions of this complex plane, right? So why don't we just position the contour along the imaginary part of our complex plane? Oh, sorry, so this is T complex plane. Okay, so this way our integral becomes the integral from minus I infinity to plus I infinity. So now let's find the constant a1. So u1 of 0 is 1. So it's equal to a1 times the following integral from minus I infinity to plus I infinity e2 t squared over 2 dt. And this is a simple Gaussian integral. It can be taken by a trivial change t is equal to is. And the answer is, so dt is I ds, so a1 I square root of 2 pi, and is equal to 1. So a constant is fixed. a1 is 1 over I square root of 2 pi. Right, once we fixed this constant, let's figure out if we can actually take this integral exactly. Well, sometimes it's possible. In most cases, unfortunately, it's not possible. So in that case, our goal would be to find some kind of characteristic asymptotic behavior of our solution. Okay, let's actually write down their exact integral. So u1 of x now is equal to the integral from minus I infinity to plus I infinity with that constant. Let's actually switch to this s integration variable. So it's 1 over 2 pi, the integral from minus infinity to plus infinity, the exponential function of x is minus s squared over 2 ds. And this is again a very simple integral. It's a Gaussian integral again, because we can shift the variable of integration. Like just let's factor out 1/2. So it's going to be s minus xi squared. So we complete the square. It's -1. Yeah, and minus x squared over 2. So if we make another change, like s minus xi is equal to pi, sorry, p, then we have another Gaussian integral, and the result, it will give the same kind of result. So it's going to be equal to square root of 2 pi. So it will cancel this square root of 2 pi, and the result will be the exponential function of minus x squared over 2. Great, so we found the first solution of our differential equation. Exactly. It's simple Gaussian exponential. And it satisfies our initial condition, so u of 0 is equal to 1. And it also vanishes at x tending to plus and minus infinity. But the following the softer condition of decay, the stronger condition of decay, is not satisfied, because the exponential function decays too fast, so the product of x times u1 of x still tends to 0. So this condition is not met. All right, let's figure out if we have some more luck with another solution, u2, which is defined, as you remember, by a simple half of this contour. So the contour goes from 0 to plus I infinity. All right, so this is the second solution. So another constant a2, and the integral now stretches from 0 this time to plus I infinity e to xt minus, plus t squared over 2 dt. Okay, so again, let's normalize our solution. So let's fix our constant a2. So if x is equal to 0, then again, we are dealing with the same kind of Gaussian integral which we encountered before. But before, it was taken from minus I infinity. Now, just half of it, because it's taken from 0. So the answer would be square root of pi by 2, all right? So u2 of 0 is equal to a2 I square root of pi by 2. And it's supposed to be equal to, so now we fix the second constant, which is 1 over r square root of 2 over pi. Great. And now our normalized solution look like this. u2 of x is equal to 1 over I square root of 2 over pi, integral from 0 to plus I infinity e to xt plus t squared over 2 dt. So this integral, as we'll see, can't be taken exactly. So we'll be interested in its asymptotics and large positive and negative x. So let's now study the asymptotics.